when we study difference equations, this neutrality with respect to the direction of time for difference equations is much more easily brought out, and you could by inference conclude that the same holds for differential equations as well. So, let us now start talking about difference equations. Difference equations relate to discrete systems in the same way that differential equations relate to continuous time systems. So, if you have continuous time systems, you describe them by differential equations. If you have discrete time systems, you would describe them using difference equations. Furthermore, if you confined yourself to linear time invariant difference discrete time systems, then you would naturally confine yourself to what are called linear constant coefficient difference equations. So, let us try to see what is the form of the general linear constant coefficient difference equation. This is the general form of the equation, all right. So, we believe that this should correspond to a system where x n is the input and y n is the output. Before we proceed further, let us try to understand how these y n minus k that we have, which are essentially shifted versions of y n, shifted by different values of k, and scaling each of them by a k and adding them up, how this really matches or resembles the earlier differential equation that we had. The differential equation we had was the following. The linear constant coefficient differential equation was n equals 0 to n a n d n y t by d t to the n equal to x t. So, for the continuous time case we have derivatives. For the discrete time case we just have shifted versions of the input, but shifting an input shifted versions of the output. Shifting an output or shifting a signal is not the same as or not even similar to differentiating it. So, why this discrepancy over here? On the one hand, we take gradients in the continuous case. Here we are not taking gradients, or so it seems. In order to understand this better, let us actually see what we would mean by the counterpart of a derivative in the discrete context. What is the derivative in the continuous case? In the continuous time case, a derivative is d, say yt by dt, and it is given by limit as epsilon goes to 0 of yt minus y t plus epsilon, or if you like t minus epsilon, whichever, divided by epsilon. What can we do in the continuous in the corresponding discrete case? Suppose we say the same thing. Remember that in the continuous time case, we want epsilon to get as close to 0 as possible in order to get a better and better approximation of the derivative, but we do not want it to become 0. Same thing is true for the discrete case as well. There we would say limit as epsilon tends to 0, this is the discrete case, of y n minus y n minus epsilon divided by epsilon. But in the discrete case, time which is represented by epsilon can either be 0 or 1 or 2 or minus 1 or minus 2. We cannot have fractional values of time, time is discrete. So, what is the smallest non-zero value for epsilon? One. So, we get, and there is no limits to be taken because there is no continuous variation here. Epsilon is clearly going to be equal to this fixed value called 1. So, this entire expression simply becomes y n minus y n minus 1 divided by 1. So, that you just get y n minus y n minus 1. This quantity is what we call, for convenience now, y dash of n. In the language of signal processing and system theory, we call this the first difference of y n, corresponding to what we would have called the first derivative of y t. Here we call it the first difference of y n. Okay. Now, what would be a higher derivative or the equivalent of a higher derivative over here? The higher derivative, second difference. Second difference or the equivalent of the second derivative of y n is defined simply as the first derivative, first difference of the first difference of y n. So, the second difference of y n, that is to say y double dash n is defined as equal to y dash of n dash, which is equal to y dash of n minus y dash of n minus 1. This is the second difference. And by analogy you can go on and define the nth difference. The nth difference will simply be I will denote this by y n of n is equal to y n minus 1 of n minus y n minus 1 of n minus 1. So, now it is clear how to get higher differences of any order. We have the first difference, we have the second difference, we have higher differences of all orders, right. So, now let us see how we got that equation for the general form of a linear constant difference system described by a linear constant coefficient difference system, this one. How did we get this? Very simple. After you add the 0th difference, which is y n itself, with some scaled version of the first difference and some scaled version of the second difference and so on up to some scaled version of the nth difference, you will get all kinds of terms, but they will all be y n minus 1, y n minus 2, y n minus 3 and so on up to y n minus capital N. This is all you will get, except that now the coefficients are all getting a little mixed up. You will have several terms with coefficients y n, you will have several terms with coefficient y n minus 1 and so on. So, you could just collect all the coefficients together and define new coefficients, and it is in fact subsequent to doing that we have got these coefficients a k over here. This completes our justification of calling this the nth order difference equation for a system that describes a system. So, let us rewrite it over here to acknowledge that we have completed our justification for an nth order system. This is what we have. And just by the side, if you are interested in knowing what is the opposite of differentiation or what is the opposite of differencing, in the case of differentiation it is integration, it is the running integral. What is the opposite of the difference of the first difference in the discrete case? That again is best addressed right now. What does integration give? Integration after differentiation returns to us the original signal. That is, if I had x t and applied it to a differentiator, I would get x dash t, where the differentiator is nothing but dxt by dt. Now, the inverse of this would be to apply x dash t over here to a system which is an integrator and get back x t. What would be the expression that described the integrator? We already know this. I think this has been discussed earlier in the course. It is simply integral minus infinity to t x dash of t dash dt dash. This would give us x t back. Now, let us see what happens in the discrete case. In the discrete case, you have x n and you apply the first difference, which we again denote by a block with a d written inside, to get x dash n. If you want to apply x dash n to a system that returns x n, then what you really need to do is to replace this, or rather to write this over here, where this actually signifies a summation from k equals minus infinity to infinity, sorry, to n o. K equals minus infinity to n x dash of k. This would be the inverse of the differencing operation. This is called, while this was called a running integral, this is what we just call a running sum. So, let us now take a look at the difference equation once again. The general difference equation was one which involved a sequence, an unknown sequence y n, which would arise out of the system as a response to an applied sequence x n. So, the x n was the forcing function or the forcing sequence or the input, and y n is the solution or the response of the system. The equation itself, if you will recall, was so this was the equation, and just as before, this we will try to associate with a system, an electrical system, where x n is the input and y n is the output. In short, we wish to determine the output y n when x n is applied as the input. The way we proceed with this exercise of discovering y n given x n and given the coefficients a k is going to be very similar to what we did in the case of the differential equation. The reason is that both are going to be linear, constant coefficient and ordinary. This in fact is something that we should always bear in mind. What we are dealing with is the linear, constant coefficient ordinary difference equation. which I will simply abbreviate by d prime E. So, when I write d E, it will be the differential equation. When I write d prime E, it will refer to the difference equation. This will make my writing a little easier, right. So, how do we solve a linear constant coefficient ordinary difference equation? The steps we have to go through are going to be very similar to those that we followed when we solved the linear constant coefficient ordinary differential equation. We start by seeing if there is any special sequence which is invariant to the process of differencing. If you recall, for the case of the differential equation, we did try to seek a function which was not affected by differentiation, and we found such a function. For the case of differentiation, we had an exponential as the invariant function. Which on differentiation simply becomes s e to the power s t. Clearly, invariance does not mean the function remains exactly the same. It simply means that the function changes only by a multiplicative constant factor. In this case, the constant multiplicative factor is s, this. Now, for the case of differencing, we shall claim that what we need is what is called the discrete exponential, of the form a r to the power n. Now, let us see what happens to a r to the power n when you difference it. We have to first check that it is indeed invariant, in short that it only alters by a multiplicative constant upon differencing, and subsequently we will see what is that multiplicative constant as well. Having established that, we will be in a position to take the next step forward with regard to discovering the solution of the difference equation. So, well, let us take a typical discrete exponential sequence. If it is of the form a r to the power n, that is to say, if this is what we call as x n, then the sequence of members of x n would be of the form a x n would be of the form a r to the power 2, a r cubed, and so on, a r to the power n, and continuing endlessly. This is what we would get, right. So, now let us look at x n plus 1. This would give us the sequence a r squared, and so on. We would get a r to the power n plus 1, and so on endlessly. Now, there are two things to recognize about these two sequences. The first is that there is a constant ratio between corresponding members of the sequence. Equals, for example, a r by a, or This is one point. Another point is the difference. What is the difference between successive members of the sequence? Let us take a look. Suppose we subtract the first member of the second sequence of the first sequence from the first member of the second sequence. We would get a r minus a, that is equal to a r minus 1. Okay. So, this is the first member of x dash n, first member. Okay. Second, a r squared minus a r, this would give us r a r minus 1, second member. So, this is actually x dash, this would be the first member we could simply directly write as x dash of 1, x dash of 2. Similarly, if you go on, you would get a r to the power n plus 1 minus a r to the power n, which is equal to r to the power n minus times a r n minus 1, r to the power n a r minus 1. So, this is the sequence you would get. You would get x dash n as the sequence a r minus 1, r a r minus 1, r to the n a r minus 1, so on, which is still a sequence that is exponential. Why is it a sequence which is exponential? Because it matches the first property, it still meets the first property that we just discussed, namely that there is a constant ratio between a pair of consecutive members. If you take the second member of this sequence and divide it by the first member of the sequence, you will get r. If you take the third member and divide it by the second member, you will get r. So, this is certainly still an exponential sequence. More importantly, it is an exponential sequence with the same r. As the original. The only thing that has changed by differencing is the factor, is the appearance of the factor r minus 1. That is the only thing that has changed. So, if since that is only a change by a constant multiplicative factor, by our criteria it constitutes, or rather this sequence, the exponential sequence, is eligible to be called an invariant sequence under differencing. What would happen if you differentiate it once again? That is, what would happen if you took x dash n plus 1 minus x dash n, which by the way, is exactly the same as x dash n minus x dash n minus 1. This is something that might have worried some of the viewers, because we started by saying that this is what we call the first difference, and later on when x dash was x n and x dash n minus 1 was x n minus 1, this is what we call the first difference. Then what happened was, we replaced x n by x n plus 1 and x n minus 1 by x n. Does that difference really matter? It does not, because whatever differencing operation we are doing it for all n. So, if you just write n plus 1 equals m, then you will get the same form as before. You will get x m minus x m minus 1 equals x n plus 1 minus x n. So, whether you do x dash n plus 1 minus x dash n at this point to get the second difference, or you do x dash n minus x dash n minus 1 to get the second difference, you can be sure that you get the same result in both cases. You are speaking of the same function in both cases. Now, there is really no need to prove that under the operation of second differencing, the exponential still remains an invariant function. It automatically will, because as far as x dash n minus 1 or x dash n plus 1 or x dash n is concerned, this sequence is also nothing but an exponential sequence. And so, if writing x dash makes us uncomfortable, we will completely rename it and call it y n. Then we are just considering then the second difference, that is to say x double dash n is nothing but y dash n, and since y n is going to be a discrete sequence, discrete exponential sequence as before, y dash n, which is x double dash n, will again remain a discrete exponential sequence. The only thing that will occur is that another factor r minus 1 will come out, so that we will now get r minus 1 squared in every member of the sequence as a constant multiplying factor. That is the only change, right. So, we have now established the invariance of the discrete exponential under differentiation, or rather under differencing. Once we have this very important fact in hand, we are ready to go on and look at the solution, look at the process of solution of the difference equation. I do not at all intend to do this in full detail, because I have already spent sufficient amount of in fact luxurious amount of time on the study of the differential equation. So, all I will now do is to keep presenting analogies with the differential equation and very quickly run through the process of solving the difference equation. Right. So, if this is the difference equation, we will first look at solving the homogeneous equation. The homogeneous equation, the corresponding homogeneous equation would be this is of course what we call the non-homogeneous equation. So, we have the homogeneous equation to look at. Now, recall what we did last time. We made use of the invariant function under differentiation and assumed that y n would have the form of the invariant function. Hence, here too we will assume that y n is of the form a r to the power n. If we make such an assumption, then it is clear that the factor a r to the power n will appear in every term of this summation, and hence a r to the power n can be factored out to leave behind just a polynomial, an algebraic polynomial in the coefficients a k. Okay. So, what we can say is that substitute this assumed solution, factor out the exponential a r to the power n, and you are left with the algebraic characteristic equation. Okay. So, all this is what we will call step 1. Step 2, I am just going to write out the steps, since most of the steps, as I said, are extremely analogous. Even step 1 is analogous to what we used to do for the differential equation when we tried to solve it for the linear constant coefficient ordinary differential equation. So, step 2, once you have the characteristic equation, solve the algebraic characteristic equation, find the roots. Fine. Now, there are several cases that can occur, as in the case of the differential equation, as it happened with the differential equation. You could have multiple repeated roots, you could have all distinct roots, so on and so forth. So, in order to avoid getting into matters of detail, I will assume for the present that we have a set of n distinct roots. If you have n distinct roots, then what you would get is a sequence of n different complex exponentials, each of which would be prefixed with an arbitrary constant. So, what you would get is essentially something of the form y n, where y n is the solution to the homogeneous equation. Please, we have still not even started on the non-homogeneous equation, is of the form summation, let us call them let us call the arbitrary constants, say C k r k to the power n. This is an exponential. C k is the arbitrary multiplying constant, and you have, since you have n roots, you have n capital N possible values of k. So, k goes from 1 to n. This is the form of the solution that you have. Now, as before, we will not stop here and start examining the arbitrary constants. It is a little too early for that. These arbitrary constants do need to be addressed, but not at this point of time. Before we start looking at them, we have to now look at the solution. We have to first look at the solution of the non-homogeneous equation. Three. Well, just go back for a minute. Okay, we have solved this and we have found the roots. So, let there be n distinct roots, then the solution is takes the form given over here. Okay. Now that we have that, we now look at the solution of the non-homogeneous equation. Now, again for the case of the non-homogeneous equation, what we do is very similar to what we did in the case of the differential equation. So, there what we had in hand was only a few cases of possible functions that we could apply as the forcing function. We confined ourselves to those forcing functions which had easy solutions, namely exponentials, constants and polynomials. We will see here too that these are the three categories of exciting functions or forcing functions for which we will approach the non-homogeneous solution to the non-homogeneous equation. So, the non-homogeneous equation is of the form a k y n minus k, k going from 0 to n, x n. Well, under differencing, a constant function x n is reduced to the identically 0 function, which you can just call 0 of n if you like, which is just the sequence 0 0 0 0, which is also a constant function. This is obvious because when you do a differencing, you take x n plus 1 minus x n or x n minus x n minus 1, and when x n minus 1 equals x n plus 1, differencing would just yield the 0 sequence. That is fine. So, this is one sequence which is invariant to differencing. Another we know of course is the exponential. The third we know, or we guess, is the polynomial. So, what is a polynomial sequence? What is a polynomial sequence x n? It is of the form say k, k n squared, k n cubed, so on. This is a polynomial sequence. We will see if this is invariant under differencing. We are really not seeing if this same sequence appears under differencing. What we are going to see is if we get a function of the same category as the polynomial upon applying the differencing operation. That is what we really have to see. Let us see if that is the case. K n minus k gives you n into k minus 1. If you take k n squared minus k n, k n minus k will give you k into n minus 1, k n squared minus k n will give you k n into n minus 1, and so on. This is what you will get. So, you get the sequence k times n minus 1 k n n minus 1 k n squared n minus 1 and so on. This is the sequence you will get, which clearly is also a polynomial sequence because it has factors n, n squared, n cubed and so on. However, it is to be seen that this sequence is not identical to the original polynomial sequence. It certainly is not, but that is not a problem. All we want is that it remains a polynomial sequence, which it does. Thus, it is only for these three cases of A constant, x n, B polynomial x n, and C exponential x n that we attempt to solve the non-homogeneous equation. A solution of the NHE with any of the above forcing functions, forcing sequences, will proceed by assuming that the solution 2 is a sequence of the same category. That the solution y n is also a sequence of the same type. So, we assume a solution of the same type and we go ahead and solve the equation, and using this we can find the solution to the non-homogeneous equation. How we exactly do it is really not necessary to go into. It is something that you can sort out for yourselves. It is very similar to what you do in the case of the differential equation. In fact, it is extraordinarily similar to that. Let us call the solution to the NHE found by this approach the basic solution to the non-homogeneous equation and denote it by psi 0 of n. Right. Now, let us just go and check what point we are at. This was point 3, solving this non-homogeneous equation was point 3, and this is the end of point 3. Now that we have the basic solution to the non-homogeneous equation, let us just add a footnote. What do we mean by the basic solution of the non-homogeneous equation? How is it different from what we have also sometimes called the complete solution? the basic solution to the non-homogeneous equation is just the complete solution in which all the arbitrary constants to be inserted into the homogeneous solution have been set at 0. So, the basic solution psi naught n to the non-homogeneous equation corresponds to the case of the complete solution to the non-homogeneous equation found by constraining all the arbit constants in the homogeneous equation solution to so if you constrain the solution all the constants arbitrary constants to 0 in the solution of the homogeneous equation, then what you get as the complete solution is nothing but psi naught. So, that is psi naught, and what you get as psi of t is the general case, the more general case psi of t. So, we are now at point 4. The complete solution psi of t takes the form y n, oh, it is not psi of t, sorry, this is psi of n, a hangover from our differential equation days. Y n equals psi 0 of n plus summation c k r k to the power n, as k goes from 1 to n, where c k are the arbitrary constants. Right. So, as long as you have arbitrary constants, even if you have one arbitrary constant, you are bound to have an infinite number of solutions. If you have more arbitrary constants than one, then you are going to have more infinite solutions, if more infinite makes any sense. It really does not actually, but all I want to point out is that you have lots and lots and lots of solutions, just like in the case of the differential equation. But the important point again is, how can a physical system have an infinite number of solutions? How can it even have two solutions for that matter? It should have only one solution. The answer again is the same as in the case of the differential equations. It is that you have to give some external help not found in the differential equation itself, to pick the correct solution out of the too many that have been supplied to you. The physical system has only one solution, and therefore, that one solution must be present in this multitude of solutions that the theory is throwing up at us, except that we have to know how to pick it up. The way we pick it up is by getting some additional information about the physical solution by in the form of settling a value for the auxiliary conditions. So, now come in the auxiliary conditions. We invoke the auxiliary conditions to resolve the problem of picking the unique solution all the mathematically possible solutions fine. So, we have to invoke the auxiliary conditions. For the first order case, for the case of a first order equation, only one auxiliary condition is required, and that auxiliary condition will be in the form of the value of the solution at some arbitrary instant of time, just like it was the value of the capacitor voltage at some arbitrary instant of time. Here of course, it is an arbitrary discrete instant of time. It does not have to be the initial condition, there also it did not have to be, here also it does not have to be. It can be any point of time along the discrete time axis at which you specify what value the solution has. The moment you do this, you have put your finger on just one solution. This takes the form of a value of the solution y n at any point of discrete time of our choosing. So, you choose any n naught and let y n take the value y naught at n naught. So, that y naught is the auxiliary condition and it is given by y of n naught. So, if you do this, you have picked a particular solution. This happens in the case of the first order system, because as in the case of the continuous first order differential equation, no two solution trajectories, though there are an infinite number of solution trajectories, no two solution trajectories ever cross each other. In the first order system, no two distinct solution trajectories ever cross each other. So, since this is the case, one auxiliary condition is enough. For higher order systems, for higher order discrete systems, different solution trajectories can cross each other and additional auxiliary conditions will be required to ensure a unique solution. To ensure a unique solution. The additional information could be in several forms. Can be supplied in several forms. Such as A, fix an n naught for a fixed n naught, for a fixed discrete time instant n naught, provide y n naught, y dash n naught, etc. That is one way of doing it. Or for different discrete time points, n naught 1, n naught 2, etc., supply y n naught 1, y n naught 2, so on. C, I will just say various other combinations. This is C, D and so on. All these are various other combinations. So, we have multiple ways of specifying the auxiliary conditions, again very similar in form to what we had in the case of the differential equation. And once you set down all the auxiliary conditions one by one, you tie down the solutions, so that you narrow down and finally land up with a unique solution. This unique solution, the final unique solution, will match the output of the physical system. right. So, that takes care of the multiplicity of solutions. I think we were somewhere in the realm of point number 4, no, point number 5, all right. So, point number 4 was about composing the complete solution. Point number 5 discussed the multiplicity problem.